Okay, well, welcome. This is one of the atmospheric highlights during the meeting, and that's the Bowie lecture. And our speaker today is Professor David Randall from Colorado State. David is, I'm sure, well known to all of you. That's why you're in this room, in fact. But David went to school at Ohio State, got his PhD at UCLA, was on the faculty at MIT, served his nation by working at NASA Goddard Space Flight Center for a period of time. Then when that was sufficient service, he went to Colorado State, where he's been since, and he's one of the most active individual in climate modeling, very active in ARM program and other national and international programs. And today, he's going to be speaking about a subject that really plays a central role not only in the science, but in certain policy debates. So today's Bjerknes lecture by Professor Randall is Testing Cloud Parameterizations Used in Climate Models Against Observations in High-Resolution Cloud Models. Professor Randall.
Thank you, Marv. Let me get myself set up here. Let's see, I flipped this. Hey, what do you know? So far, so good. Thank you very much for the introduction, Marv. And I changed the title slightly. The subject is basically the same, but cloud parameterizations and high-resolution cloud models. So I'd like to begin by trying to make some connections between this subject and Jacob Bjerknes, and that's actually rather easy to do, although most people think of Bjerknes today in connection with his amazing work on El Nino back in the 60s. He did a lot of other amazing things in his career, and one of them is reported in this little paper that came out in 1938. And I'm not sure how many of you may have read this paper, but I'm sure most of you, if not all of you, have read about this paper because the work he did here is actually textbook material now and has been for quite some time. In a nutshell, what he explained is why cumulus clouds organize themselves so that the updrafts are very narrow and intense and there's a broad subsiding environment around them. And I'll just summarize that very quickly with this slide, and it will feed into the rest of the talk. The scenario is we have a conditionally unstable sounding, so the moist adiabatic lapse rate is here, the actual lapse rate is the black line, and the dry adiabatic lapse rate is the red line. So this is conditional instability, and under these conditions, if we have a moist updraft, that will tend to warm the updraft air relative to the environmental sounding. And if we have a unsaturated downdraft, that will tend to warm the subsiding air relative to the environmental sighting. So both the ascent, the moist ascent, and the dry descent warm. But in order to have a functional cloud, what we'd like to do is make the updraft as warm as possible relative to the descending air. And Bjerknes' insight, which he demonstrated through a simple mathematical argument that I won't give here, is that you maximize the buoyancy of the updraft by making it fast and narrow, hence the long blue arrow here, and by making the downdraft then, to compensate for that upward jet, make the downdraft very slow and broad. And this, in a nutshell, is why the tropical atmosphere looks much the way it does. And this work was actually very influential, and I got some input from several people. Now, obviously, I couldn't ask Charney about this today because Charney, unfortunately, has passed away 20 years ago. But in a book about Bjerknes' work, there's this quote from Charney, in which he says that Bjerknes' work on moist convection was one of the keys to Charney's insights about the development of hurricanes and the cooperative interactions between the convective clouds and the larger scale tropical cyclone circulation. Doug Lilly says that his thesis work, essentially, his dissertation work, published in 1960, was to some extent based on ideas taken from Bjerknes' paper, which is often called the slice method for reasons I don't understand. And finally, Ako Arakawa said that Bjerknes' insight into the moist updraft and slowly subsiding broad environment was the impetus for his concept of the mass flux cumulus parameterization, which today is almost ubiquitous in general circulation models. So a very influential paper by Bjerknes in 1938 on this subject. It's a little bit anomalous, this is my impression. When you look at the body of Bjerknes' work, almost all of it deals with large-scale circulations one way or another. And it's difficult for me to understand how he became interested in this problem, how he arrived at the concept, and what he thought of it later on in his career. He wrote papers in the 60s about the Hadley circulation, and there are actually some cloud analyses done with early satellite data from those days. But let's move now from that introductory link to Bjerknes into the main subject of the talk, and this, of course, is the problem that we're all aware of, that deficiencies in the representation of cloud and radiation processes in climate models are the primary drivers of the uncertainties surrounding predictions of climate change, anthropogenic and otherwise. The depressing fact is that this was already true and already recognized to be true, at least by some people, 30 years ago in the early 70s. It's still true today, and it will probably still be true 30 years from now. And the question is, what can we do about this? How can we break out of this, this trap? So what I will talk about now, briefly summarized here, is first I'll give you a perspective on the cloud parameterization problem. I know most of you here don't actually work on that subject, so I'll just give you a kind of a introductory overview of why it is such a problem. Talk a little bit about how high-resolution cloud models, cloud system resolving models, and also single-column models can be used in cloud parameterization research, and then say something about future directions. So this picture I could have shown in connection with Bjerknes' paper on the slice method. He essentially recognized that deep cumulus convection prefers to organize itself in the form of these hot towers with a slowly subsiding environment in between. And Reel and Malkus, back in the late 50s, deduced from observations that these hot towers are essential for the upward transport of energy in the tropics. And of course, today we recognize that they're also essential for the transport of moisture into the middle and upper troposphere, and for momentum transport and many other things. So we have then the concept of the environment, essentially, which follows from Bjerknes' insight, that the thermodynamic properties of the slowly subsiding environment are in fact very nearly the same as those of the large-scale mean, simply because the convective towers occupy such a small fraction of the total area. And this idea has been extensively used in cumulus parameterizations, as I mentioned earlier. This is at the core of the mass flux concept that almost everybody is using now. We also have convective downdrafts, and not long after the first papers on convective mass flux parameterizations came out, people began pointing out that we don't have only these narrow, warm updrafts in the cumulus towers. We also have narrow, rather strong downdrafts, which are driven largely by the evaporation of precipitation. And so these tend to lead to a cooling and moistening of the environment. And so far, up to this point, we have the narrow updrafts, we have the broad subsiding environment, and we have now convective scale downdrafts. And next, we have to recognize that besides the convective clouds, there are also stratiform clouds out there. And the earliest work on this subject in a climate modeling framework was by Smagorinsky, 1960 paper proposing a parameterization of stratiform cloudiness based on relative humidity. And in fact, for many years, and to some extent even today, general circulation models essentially have parameterized stratiform cloudiness one way or another in terms of the relative humidity at the resolved scale. But we know that in reality, stratiform clouds are produced largely through outflows from convective towers. That's one of the most important ways to make stratiform clouds in the Earth's atmosphere, especially cirrus. And so we need to make the connection between the cumulus parameterizations in our models and the stratiform cloud parameterizations. And today these connections have been made, and the hook that's used for this basically is the detrainment of condensed water, which was first incorporated into the cumulus parameterization of Arakawa-Schubert in 1974. So following the lead of Sundqvist in the 80s and more recently in very many places during the 90s, large-scale modelers have begun to actually predict the spatial distribution of both liquid and ice in the atmosphere, in addition to vapor, of course. And in most of these models, there is now an explicit convective source term for the condensed water of the stratiform clouds. So it took about 20 years, maybe not 30 years, but 20 years to begin making use of the conceptual hook in the Arakawa-Schubert paper. Probably the most advanced parameterization of this type today is the one by Tietke. That's my opinion anyway. He predicts, in addition to the cloud mass, the cloud area. And this is more or less a continuity equation for the cloud air, if you like. So cumulus detrainment acts as a source not only for condensed water mass, but also for cloud area. And the literature shows that this type of parameterization has in fact led to major improvements in both NWP scores and climate simulations. And so this type of thing does represent progress. And it's important to note this because I often hear people asking whether anything is ever getting better in the field of cloud parameterization, and it is. But there are a lot of major problems that have hardly been addressed at all yet in the framework of large-scale modeling, and probably the biggest one is the mesoscale. Everybody knows that deep convection and even shallow convection often organizes itself in these spectacular mesoscale structures, and that this has got to be very important for the dynamics of the individual cumuli growing in there, first of all, but also because the mesoscale structure itself entails circulations and microphysical processes and obviously a strong radiative impact and all sorts of things that we need to get in the models, and it's not there. There are basically two views of the mesoscale. This is my characterization of the literature. First of all, we have the papers by Bob House and others that emphasize things like the growth of anvil clouds from convective detrainment, the precipitation from the anvil clouds, the stratiform precipitation, and then also vertical motions, upward motion in the upper part of the anvil, downward motion in the lower part of the anvil. And Leo Donner and others have been trying to incorporate this type of idea into general circulation models the last few years. In addition, of course, we have the work by Mitch Moncrief and colleagues that emphasizes the sort of dynamical aspects of mesoscale organization, squall line structures essentially. And the reality, of course, includes both of these things, so we would hope that down the road somewhere these two streams of work can come together. At the present time, we're just beginning to include this sort of thing in climate models. So we have updrafts, environment, downdrafts, mesoscale. Now we come to turbulence. Virtually all clouds are turbulent. Anybody who's flown anywhere knows that. And turbulence is one of the most important things regulating fractional cloud cover. It certainly matters in many other ways, but this is the first thing I think of, that the holes in stratiform clouds especially tend to be associated to a large extent with what you could call convective turbulence in the cloud layer. So if we're interested in fractional cloudiness and we're interested in the optical properties of this structure here, we need to know about the turbulent motions in the cloud. And of course, those motions also produce fluxes. The most important paper about this subject, in my opinion, is the one by Doug Lilly back in 1968, in which he recognized the extremely close interactions among cloudiness, turbulence, and radiation. And in fact, parameterized radiation and turbulence together as essentially a single tightly coupled process in the context of boundary layer stratocumulus clouds. There are some GCMs today incorporating Lilly's model, Lilly's ideas, and there are other models working to do so. But so far, to the best of my knowledge, these ideas are really only being used in the original context, that is boundary layer clouds. But the processes that Lilly discussed are going on in cirrus clouds and virtually all of the types of stratiform clouds as well, and this is just not being recognized at the moment. We also have microphysical processes. There's a little picture of snow falling out of upper-level clouds, beautiful fall streaks. To the extent that there were lower level clouds under these things, we'd have to worry about the fall streaks falling through clear air or cloudy air, and that would have to be incorporated into a parameterization in a statistical way, of course, because a cloud parameterization in a large-scale model does not depict these individual cells. It only gives you some statistic, like the average cloudiness, the total amount of water, and so on and so forth. And one of the main challenges of cloud parameterization as it's done today is to try to incorporate important things like the scavenging of lower-level cloud water by ice falling from above, let's say, when all you really have to work with, all you have to go on, all the input that's available to you is some statistical information about the cloud field. In addition, of course, while we're on the subject of microphysical processes, the number of cloud particles per unit volume is very, very important radiatively, and this is influenced by the ambient aerosol, and that depends on chemical processes and so on. Now, I was at a meeting a few weeks ago in Fort Collins at which a number of radiative transfer specialists, whose identities I will protect here, stated openly in the meeting that from the point of view of large-scale modeling, the radiative transfer problem has been solved in the sense that accurate radiative fluxes can be computed even for cloudy skies provided that the input is known. And of course, the main issue then is the required input. This doesn't really mean that there are no remaining issues, but what it means is that the primary issue now is getting the right input to the radiative transfer parameterization. The input, the flaws in the input, are driving the error that comes out of the radiative transfer code. And that's probably been true for a long time, I would say. The information that you need includes, of course, information about the nature of the cloud particles, but also information about the cloud geometry, such things as radiative overlap, but many more. So the picture I'm painting for you, just to pound it on your head, is overwhelming complexity. That this problem is taking a long time to solve because it is hard. And this is a summary of what I've just been saying to you. I won't run down all the bullets here, but I've listed these various things as all being important in some sense, and only the top few are incorporated in any meaningful way at all in existing models, and the rest of them are still in the future. So one of the questions we have to ask ourselves, and a question that I suspect we prefer to avoid most of the time, is whether we can really do this. How well can we do it? Let's put it that way. To the extent that we require quantitative accuracy of the Earth's radiation budget and various hydrological processes tied up with clouds, can we really calculate these things in a large-scale model with the kind of accuracy that we need to do climate change problem? I don't want to say that it can't be done. I like to think that it can be done. I'm trying to do it. But I've been trying for a long time, and I don't expect to succeed in my lifetime. So I think it's going to take quite a long time to kill these problems. And we've already been working on it since the 60s, and we're still in the early stages. In fact, a week or so ago in a meeting in Goddard, Akio Arakawa said that cloud parameterization is a very young subject. So we began around 1960, we're now at 2001, and there's a big future in front of us. This blue arrow should probably extend way over there, and that would be about where we'd solve the problem. Before going on to talk about the role of high-resolution cloud models, I'd like to just sketch in two view graphs some ideas of a work in progress that can be viewed as a sort of current state-of-the-art attempt at cloud parameterization for a large-scale model, and this is really an extension of the parameterization developed by Michael Kika that I mentioned earlier. This is supposed to be a plan view looking down, let's say, on the grid box of a large-scale model, and this blue line separates a cloudy region on the left from a clear region on the right. And then this blue circle here represents a convective updraft, or actually all of the convective updrafts in the box. And I've drawn it on the boundary between the cloudy and clear air because I'm thinking that the cloud is formed largely by convective detrainment, as indicated by this arrow, so that the outflow from the updraft goes into the cloudy region, more or less by definition. I've also shown that the updraft is entraining air from the cloudy region and the clear region, and that there's a convective downdraft here that's entraining, as I've shown it anyway, only from the clear region. And in addition to that, although the graphic doesn't show this, I want to think of the cloudy region as being turbulent and the clear region as being less so. And we have to recognize that besides the fact that the cloudy region contains cloud water or ice and the clear region presumably doesn't, they may also have other differences in the thermodynamic properties. They certainly have different water-vapor mixing ratios, and they may also have different temperatures in principle, although it's usually assumed that they don't. So how could we approach this? Well, again, I don't want to actually describe a parameterization here, but just to give you a feeling for how you might approach this. You can try to introduce a lot of prognostic variables. Prognostic mainly because that's the easiest thing to do. Easier to solve time-stepped equations than big boundary value problems. Prognostic variables representing the subgrid scale variability, the unresolved variability on multiple scales inside the GCM grid box. So you have the water vapor and temperature in the clear and cloudy regions. You have cloud water and ice in the cloud only. You have the area covered by the stratiform cloud, which of course is part of Typke's scheme. You have the masses of rain and snow, and you might also include more information about the particle size distribution and other species like Graupel and so on. You have the convective mass flux. You have a mesoscale mass flux, a la Bob Howes and colleagues. And then, of course, you have the turbulence in the stratiform cloud, which is important because it's going to be one of the things that makes that cloud go away eventually. Turbulent fluxes, turbulent variances, and so on in multiple regions, in the cloudy region, in the clear region, in the convective tower, and so on. And this is all very, very complicated. It's overwhelmingly complicated. And in fact, if you start counting degrees of freedom and considering all the covariances and variances and so on and so forth, you find that the number of degrees of freedom is roughly comparable to the number of degrees of freedom that you would have in a cloud resolving model. But of course, here you're only talking about statistics. You don't have actual geometrical information about the shape of the clouds and so on. And despite the complexity here, there's nothing about a physical parameterization of cloud overlap in either the radiative or microphysical senses, or microphysics parameterization with aerosols, all the rest of it. So this is still a very incomplete concept. So it's easy to make it complicated because all we have to do is look out the window. But the question really is what not to put in. Which of these things can we neglect? Well, we're already neglecting a large fraction of them. So maybe that's the wrong way to think about it. But how about thinking about it in terms of prioritization? What is the next thing to put in? What should we be working on? Is it the mesoscale? Is it the turbulence in the cirrus clouds? Is it the aerosols? There are all kinds of possibilities. And the trick is knowing what to leave in and what to leave out. So we may hope, going back to the question of parameterizability, that it will be possible in the future to make a parameterization that is a lot more realistic than anything anybody has today, but not much more complicated. That would be wonderful, wouldn't it? But there's absolutely no guarantee that that can be done. And I personally doubt that it is possible. And that my reasons for doubting it are implicit in what I've been saying to you. So now we bring in the high-resolution models, which I want to call cloud system resolving models. They're cloud system models because they don't represent individual clouds. They represent many individual clouds over many cloud lifetimes. But they're cloud resolving in the sense that the resolution is fine enough to represent the structures of individual large clouds, like cumulonimbus clouds. So we have cloud system resolving models, which I've just explained, and also single column models, which are essentially the column physics components of general circulation models, the physical parameterizations, surgically extracted from the GCM and driven offline essentially by observations. So both types of models can be driven by data. Essentially, you tell one of these two types of model what the weather is by inputting the information from observations, and then let the model tell you what's going on in the cloud field. And of course, when you're driving these models with data, you are not allowing feedback because the observations are the driver. But these models are normally run inside GCMs and essentially provide the feedback there in that context to make the weather evolve in the large-scale model. So one way to think about the cloud system resolving models is that they're sort of superparameterizations. They're very complicated parameterizations in the sense that they have many degrees of freedom. But in another way, they're not so complicated because they're based on the equation of motion, for goodness sake. And the equation of motion is relatively simple. We understand it. When you start trying to represent mesoscale cloud system in terms of statistics, we don't understand it. Okay? So in fact, this is in some ways more approachable than this. I've already explained this. So some background on cloud system resolving models. The earliest work of this type that I know about was done by Yamasaki in the 1970s in the context of tropical cyclone modeling. Kruger, Arakawa, and Shu and others began working in this mode during the 1980s, middle 1980s, applying this type of model to the parameterization of convection, first of all, and later to the parameterization of stratiform cloudiness. And there are a number of papers out there about this. And the idea has caught on. So today we have dozens of these models at various centers around the world. Until recently, they've all been two-dimensional because of the computational cost, but now we can do three-dimensional cloud system resolving models depending on the application. So how do we use these models? You commonly hear that the models are used, can be used, should be used to develop parameterizations, and I would claim that that is not really true. Simply because building a high-resolution cloud model and running the high-resolution cloud model and looking at the output, making some plots, writing a paper, and so on, does not give you the ideas that are necessary to develop the parameterization that you need for the large-scale model. So a better way to think about the cloud system resolving model is that it's a tool that can be used to answer some of the questions about parameterizations that come up in the framework of large-scale modeling. They can also be used, of course, to compute detailed answer to idealized questions like how does the Walker circulation work? And there are papers in the literature like that in the last few years. We might wonder whether there's any other way to use them. This is a schematic that connects with what I've just been saying. It's a wiring diagram that shows how various communities of scientists can interact together within the framework of the GUX Cloud System Study, which is currently chaired by Steve Kruger of the University of Utah. And the key thing I want to mention here, without going through the whole diagram, is that the large-scale modeling community, here labeled the GCM single-column model community, is asking questions of the cloud system resolving modeling community and also the data community, and those questions are then answered. So we have a two-way flow here, and the important point is that it's not a one-way flow. It's not a flow of information from the cloud system modeler to the large-scale community. We have to have these questions, otherwise progress is not made here. Now, it is a fact, we can say now, that cloud system resolving models give better results in comparison with data, when driven by data, than single column models do. And you would certainly hope so, considering that cloud system resolving models are high resolution models, which are, compared to single column models, many, many times slower, more expensive to run, and of course the volume of output is larger, and so on and so forth. But nevertheless, despite this sort of a priori reason to expect better results, we have to go in and demonstrate that it's true. And this has now been done. And I'll just show you very quickly three pieces of evidence to support that claim. Here we have simulations of water vapor as a function of height. The units are grams per kilogram along the horizontal axis in both panels. And what's plotted here are errors. The exercise, the computational exercise, is to drive cloud system resolving models on this side and single column models on this side with observed weather fluctuations at the Southern Great Plains ARM site and compare the results that come out with the data. So errors are plotted, 0 is good, and you can see that the errors of the cloud system resolving models are considerably smaller than the errors from the single column models. The same is true for temperature, similar plot for temperature. And finally, cloud amount, cloud occurrence. This is not an error plot. These are plots of actual cloud amount. You probably can't read the numbers, but that's 0, 20, 40, 60% cloud amount as a function of height from the surface to 15 kilometers. And you're seeing a black curve like there, which represents observations from millimeter cloud radar. And the three panels here are three different episodes, three different several-day periods that are being analyzed. So here are the results from the cloud system resolving models. the agreement with the observations, at least in some cases, is relatively good. In fact, in all cases, it's relatively good compared to what you see over here from the single column models. So, given these better results, which should be expected given the expense, isn't it a shame that we can't run a global cloud system resolving model? Can we ever do that? Well, existing models used for climate simulation, atmospheric models, typically have about 10,000 or so grid points, roughly grid columns, roughly 200 kilometers wide. And that covers the Earth, okay? And if you wanted to go to cells or grid columns 2 kilometers wide instead, which would bring you into the cloud resolving regime, you would need about 100 million grid columns, roughly. So you end up with enormous storage, and of course the high-resolution model is going to have to take much smaller time steps, something like 100 times smaller than current GCMs. So you're looking at 10 to the 4th, that's the ratio of 10 to the 8th to 10 to the 4th here, 10 to the 4th times as many grid columns and about 100 times as many time steps per day or per year. So you're looking at about 1,000,000 times as much computation, roughly. If you assume that Moore's law, which says that computer power doubles every 18 months, continues to hold forever, which is, of course, highly questionable, then in something like 30 years, it will actually be possible to do this at roughly the same level of effort that we expend today on climate simulation with the models we have now. But 30 years is a long time, and that may be an underestimate of the reality, because Moore's law may make down on us. In the meantime, there is an alternative, SuperParameterizations, which I will now explain. This is an idea that came from Wojtek Grabowski, who is at NCAR M3, and he and Peter Smolarkowicz had the idea to incorporate Wojtek's two-dimensional cloud system resolving model as essentially a superparameterization inside Peter's anelastic global model. The global model is not really a general circulation model in the sense that it doesn't include realistic heating, it has globally uniform sea surface temperatures, no topography, and so on, but it is global. And Wojtek obtained some very interesting results, which have been published in several papers now. In the tropical part of the domain, he obtains, after a spin-up, this is time increasing down here in longitude across, so it's a Hubmüller diagram, he obtains eastward propagating, essentially wave number 1 disturbances, which he has analyzed in some detail and look very much like the Madden-Julian oscillation in the real world. And that, of course, is something that it's very difficult for most or even all general circulation models today to do. So this looks very intriguing, looks encouraging. Obviously, a lot more work is needed to explore this. But my colleague Marat Krutenov and I at CSU were inspired by Wojtek's work to embed Marat's cloud system resolving model, his own model, as a superparameterization into the atmosphere submodel of the community climate system model, which is now called the CAM, Community Atmosphere Model. And this global model, of course, is a real atmospheric GCM with realistic topography, sea surface temperatures, and so on. And so in Marat's work, the cloud system resolving model takes the place of both the stratiform and convective cloud parameterizations of the CAM. And in the future, we expect to also replace the boundary layer parameterization. And here are some results. Now, because it's very expensive, and you're all wondering about that, and I'll come to that in a minute, because it's very expensive, we were only able to do a 2-month simulation. The GCM was run at T42, which is sort of the usual resolution for climate these days. And what we have here in the top 2 panels are precipitation on the left and precipitable water on the right with the superparameterization, a control run with the conventional parameterizations of the model, and some observations for comparison in the bottom panel. And I don't want to claim anything spectacular here, except that with no tuning at all and with only about 1 month of work in terms of connecting the 2 models together, Marat was able to obtain results which are arguably as good as the results obtained with the conventional parameterizations in the CAM, and perhaps better. And the paper's in GRL earlier this year if you want to look it up. So what are we claiming? Well, not very much. The claims we're making are modest at this point. First of all, Wojtek's results suggest that superparameterizations can enable more realistic simulations of such things as the MJO, but of course a lot more work is needed. The results that Murat and I obtained demonstrate by example that it is in fact possible to incorporate a cloud system resolving model into a GCM as a superparameterization in the year 2001. And that this can actually be done without too much work, provided that the individual doing the work is familiar with both of the models when they start. There are, of course, in addition to that, a lot of a priori reasons to believe that superparameterizations can provide more realistic and more reliable simulations of climate, and I will list some of those for you. So what we get, one, you get an explicit representation of deep convection, including mesoscale organization. You get things like squall lines. All the dynamics is there. You get downdrafts on both the mesoscale and convective scale. You get anvil clouds. You get explicit fractional cloudiness. You get cloud overlap in the radiative sense and cloud overlap in the microphysical sense. You get things like convective enhancement of the surface fluxes when a gust front blows over the ocean. It might be possible to incorporate explicit multidimensional cloud radiation effects. I've had some conversations with Howard Barker about this, and we're actually going to try to do this. And of course, you also get convectively generated gravity waves, which many people now think are important for the QBO. Most of these benefits are valuable even in undisturbed weather regimes, so you shouldn't think of the superparameterization as being something that you only turn on when you have a squall line. It can do fractional cloudiness, wispy cirrus above fair weather cumulus too, and that's also useful. In addition, people often talk about the issue, how should we change the formulation of our cloud parameterization or other parameterization when we change the resolution of the GCM. When you're parameterizing these things by using a model that resolves them explicitly, there's not much of an issue about changing the formulation of that scheme as you change the resolution of the model, at least provided that the domain size of the GCM grid is big enough. You also get the ability to compare global model results on such things as the statistics of mesoscale and microscale cloud organization, things like the third moment of cloud ice, let's say, with observations from new platforms like CloudSat that are coming along in the near future. And following from that point, you could conceivably use this type of approach to enable the assimilation of such cloud statistics based on high-resolution observations. And one more bullet I forgot to add is that you get information about the small-scale spatial variability of the precipitation rate, which is important for things like runoff and flash floods and so on. I guess flash floods are runoff. But there are lots of problems that don't go away, and I have actually 2 or 3 view graphs to list those too. These are the big ones. First of all, microphysics, radiative transfer, and turbulence, including small cumulus clouds, still have to be parameterized. But having higher resolution in the cloud system resolving model surely makes that type of parameterization more tractable in each case. Remember, when you're using a conventional parameterization in the GCM, all the information you have, at best, if you're lucky, are statistics about such things as the mass of cloud or the cloud amount layer by layer in the model. You don't have any information at all about any details on the smaller scale. And of course, in addition to these things, we still have all the usual issues related to the numerical simulation of large-scale dynamics. There are also some smaller issues, well, not really small, but more technical in nature. For example, consistency between the GCM, the host GCM, and the cloud system resolving model. Are they thermodynamically compatible? Do they obey the same thermodynamic equations and other things? What's the best way to tell the cloud system resolving model what the GCM is doing and vice versa? How should that communication be handled? What about lower boundary conditions? The Earth's surface is not uniform. We have variable albedo, we have orography, we have lakes, and so on and so forth. How should that information be incorporated? Well, that's a real problem, but on the other hand, current models basically don't do anything about that at all. So it's not any worse. What about the dimensionality of the cloud system resolving model? Should it be 2D or 3D? And if it's 2D, how should we orient it? That can be explained with this little diagram. Here's a two-dimensional cloud system resolving model embedded in a GCM grid box looking down from the top, and the CSRM has been oriented east-west. Here it's been oriented north-south. Now these two configurations are going to give different answers. And Grabowski has actually addressed this in some experiments in his work, so I refer you to his papers. You could conceivably include a couple of orthogonal models. It's only a factor of 2. Or perhaps best, you could allow the same number of degrees of freedom but arrange them in a 3-dimensional array instead of a 2-dimensional array. That remains to be explored. Additional technical issues. What about the resolution of the cloud system resolving model? Grabowski's experimented with 2 kilometers and 4 kilometers. We've used 4 kilometers at CSU. Those are big numbers. Those are coarse. We have some evidence that those resolutions are fine enough to be useful, but a lot more work is needed on this, and certainly we would like to use finer resolution if we could. But the trade-off is against increasing the number of grid columns in the cloud system resolving model, or for that matter, increasing the resolution of the GCM. What about lateral boundary conditions? All the work that's been done up so far has used periodic lateral boundary conditions on the cloud system resolving model. That means that you cannot let the squall line propagate from one grid column of the GCM to the next one, as it should. So what do we do about that? I don't know. What about, and this is really the same thing I just said, what about communications between GCM grid columns? And finally, I already mentioned this, but do we need to do this everywhere all the time, or could we just turn it on in certain places at certain times? There are all these issues, and you can probably think of this many again, but none of these are showstoppers. We can, in fact, proceed down this path and learn as we go. Now, what about running it? In the work that Murat and I did, the SuperParameterization slows down the GCM by a factor of 180 relative to the model with the conventional parameterizations. And when I first saw this number, I thought, oh, 180. And then I thought, well, that's not so bad, really. You get a factor of 180 out of Intel or whoever in about 10 years or so. 10 years goes by in the blink of an eye. We can certainly do this in the not too distant future, and in fact, using the most powerful machines available, we can actually do it today. So let me try to make that argument to you. And what Murat and I did with the CSRM, we were using, as I told you, a T42 version. It was running on 64 processors of an IBM SP. One copy of the cloud system resolving model took 30 seconds per simulated day, 100 copies per GCM column, so you've got 3,000 seconds per day, and that's basically driving the runtime, so the whole model takes about an hour a day. And the time used for the actual GCM is not important in this context. So with this configuration, if you wanted to do a simulated century for climate change, it would take about 4 years, 24/7, as they say. And that's too long. We have to knock it down to a couple of months. Okay? But we can be rescued, at least in principle, by massive parallelism, because the cloud systems resolving models running in different grid columns do not communicate with each other. That part of the calculation is perfectly parallel. So we can defeat Amdahl's law in the same way that other people have defeated it in the past, essentially by making the problem a lot bigger. We add a lot of complexity in the physical parameterizations rather than increasing the resolution of the GCM as a whole. 10 years ago, 1990, we could not have even tried this. It was completely impossible. Today, we can do it, but it's hard, it's expensive. 10 years from now, it won't be a problem. Nevertheless, I think that there are several important continuing roles for conventional cloud parameterizations. Conventional parameterizations are still going to be used whenever very large computing resources are not available. If you want to do a run on your workstation next year, you will not do it with the SuperParameterization. Conventional parameterizations will still be needed for the foreseeable future for very long simulations. Sometime in the next decade or so, somebody's going to do a Milankovitch cycle with a general circulation model, climate model, and that won't be done with superparameterizations in the next 10 years. And most importantly, this last item, we will still need conventional parameterizations essentially as encapsulations of our understanding of how all of this works in a statistical sense. So we can think of the diagram I showed earlier where it had a question mark out here. I want to argue that the conventional parameterization pathway continues into the indefinite future, but starting now, the option of superparameterizations is there, and this will be explored. You may not explore it, but I will, and other people will. It's going to be explored. So, summary and conclusions. First, I wanted to slide these on, but I'm using Acrobat instead of PowerPoint, so I can't do that. It's time to start talking about, stop talking about cumulus parameterization problem and really start talking about the cloud parameterization in a more unified way and begin thinking about parameterizing cloud systems instead of separately parameterizing the convective and stratiform clouds. And we have moved a long way in this direction. We need to finish the job. And that, I think, is on the current agenda in the context of conventional parameterizations. What this is driving, of course, is a decrease in the modularity of our models. We aren't going to have a stratiform cloud module anymore and a convective cloud module anymore. We're going to have a cloud module anymore. And there are more things like this that I won't list here. But I see models as being driven towards less modularity rather than more in the future. So I'd like to say that models should be as modular as possible, but not more so, or not more modular than nature. Now, I think that for the reasons I've given, to go very far beyond where we are now with conventional parameterizations, we are going to have to make them very complicated. And they may still be less complicated than cloud system resolving models if you measure the complexity just by counting prognostic variables. But they will be more complicated in the sense that understanding how to formulate the problem and understanding how to solve the equations will actually be harder. I've shown you that when driven with data, cloud system resolving models produce much more realistic temperature, water vapor, and cloud distributions than single column models. And Steve Kruger, Rick Cedarwall, Minghua Zhang, and I are writing a little paper to make this point. A cloud system model can, in fact, be used as a superparameterization inside of GCM. The existence proof is out there. We've done it. This is, of course, a very expensive way to go, but it is a revolutionary approach in the sense that it is not simply the same kind of thing we've been doing except better. It is a different way of approaching the problem, and a way that we could not have approached it until just about now. 10 years ago, we couldn't even try this. A model using a superparameterization is 2 to 3 orders of magnitude, depending on the details, of course, more expensive than the same model with conventional parameterizations. But if we think that the climate change problem is important, if we think it's a $1 trillion economic problem, then we should seriously consider this. And it's what the program people like to call a grand challenge problem. It's a problem that will make all the computer centers very happy. A GCM with a superparameterization, because of the very high parallelism, can make use of thousands of processors with good computational efficiency. A good way to use those machines in geophysics other than image processing. And it would, in fact, be possible today to do climate change simulations, meaning something on the order of a century, using atmospheric GCM with superparameterizations coupled to an ocean model and a land surface model and so on today's most powerful machines. It would be just barely feasible. And I would argue that the cost is not out of line with the importance. So trying to tie back now to the beginning of the lecture, Bjerknes' analysis of saturated updrafts was really the starting point for the modern approach to cloud parameterization, and I tried to prove that to you by showing you the testimonials from Charney and Lilly and Arakawa at the beginning of the talk. In particular, Bjerknes' work forms the foundation for the mass flux approach to cumulus parameterization, and even if 10 or 20 years from now superparameterizations become the norm, it will still be true that the mass flux concept explains a lot of the physics that's going on in cloud systems, and it will still be useful, at least in a conceptual way. And so the sorts of research we're doing today, trying to understand things like, for example, how variations of cloudiness in the atmosphere affect the ocean and how all of this works with ENSO and other coupled ocean atmosphere phenomena that are just being uncovered in the past few years or decades, is really making connections between Bjerknes' anomalous paper on moist convection and his other great works on such things as ENSO. And I guess that was the last one. Thank you.